In July 2025, physicists at the National Institute of Standards and Technology completed the most precise clock ever built. It measures time to the 19th decimal place. The previous record was the 18th decimal place, which was already so accurate it bordered on the absurd. But the moment this clock became precise enough to actually matter, it told them something they were not prepared to hear. The fundamental constants of nature, the fixed numbers that hold all of physics together, might not be fixed. They might be drifting, slowly, nearly imperceptibly, but measurably. So you build the most accurate instrument in human history, and the first thing it tells you is that the rules of physics may not be rules at all. They may be tendencies, local habits of a universe that is still in the process of becoming what it is. That is where we begin, not with a theory, with a measurement, and with numbers that do not add up. Before going further, there is a question worth sitting with. What is a clock actually measuring? Not how it measures, we know how. Pendulums, atomic oscillations, electron transitions between energy levels. But what is the thing it is pointing at? When you glance at a watch, you assume it is registering some property of reality that exists independently of the watch, something called time. Something that flows, passes, accumulates, cannot be reversed. And that assumption feels so obvious that it barely registers as an assumption at all. Here is the problem. Physics does not have a clean definition of time that is not circular. Every formal definition either uses time to define time or borrows from everyday experience and dresses it up in equations. Newton called it absolute, flowing uniformly everywhere, independent of anything external. Einstein dismantled that in 1905, but what Einstein replaced it with is not a definition. It is a description of how time behaves under certain conditions, how it stretches near massive objects, how it compresses with velocity, how it weaves into space to form a single geometric fabric. That is different from knowing what it is. Carlo Rovelli, one of the physicists who has spent more time on this question than almost anyone alive, put it plainly. We know an enormous amount about how time behaves. We do not know what it is. Those are not the same thing. And that gap between behavior and identity is exactly where the experiments start producing results nobody expected. So when that clock in Boulder suggested the constants might be drifting, the disturbing part was not the drift itself, it was the question underneath it. If the constants are changing, what are they changing with respect to? What is the thing they are moving through? And if that thing is time, then time has just become more fundamental than the laws of physics. Not a consequence of those laws, the thing those laws happen inside, which inverts everything we thought we understood about the relationship between physical law and physical reality. The first crack in our picture of time showed up in 1971, and it was not subtle. Joseph Hafele and Richard Keating loaded cesium atomic clocks onto commercial passenger flights, not specialized research aircraft, just ordinary planes, flew them around the world, and then compared them to identical clocks that had remained on the ground. The clocks that flew came back different, not broken, not malfunctioning. They had simply measured a slightly different quantity of time than the ones that stayed still. The airborne clocks lost approximately 59 nanoseconds relative to the ground clocks, matching almost exactly what Einstein's general and special relativity had predicted. The main result was clear: time is not the same everywhere. Move through space, accelerate, change your altitude in a gravitational field, and you move through time at a different rate than someone who stayed put. This is not a metaphor. Two objects, same starting point, same ending point, different amounts of elapsed time. If that seems familiar and therefore manageable, consider what it actually means. There is no single universal clock ticking in the background of reality. There is no master time that everyone shares. There are only local clocks, local rates, local experiences of duration. The universe does not have one timeline. It has as many timelines as it has objects moving through it. And this is not abstract physics. It is already baked into the infrastructure you use every day. Your phone knows where you are right now because of GPS satellites orbiting at about 20,000 kilometers altitude. Those satellites carry atomic clocks, and because they are moving fast and sitting higher in Earth's gravitational field, those clocks run faster than clocks on the ground by about 38 microseconds per day. 38 microseconds sounds like nothing, but GPS works by calculating your position from tiny differences in signal arrival times from multiple satellites. The math is exquisitely sensitive to timing. If engineers did not correct for that daily drift, the position errors would accumulate at roughly 11 kilometers per day. Your navigation would be useless within hours. So every GPS device on Earth, every time you ask your phone to route you somewhere, is silently applying a correction derived from the fact that time runs at different rates depending on where you are. The engineers did not debate the philosophy of time before building the system. They did the calculation, applied the correction, and it worked. Time really does behave this way. The question is not whether it does. The question is what we are actually measuring when we measure it. In 2021, something happened that almost never gets reported outside specialist journals. A team at Gila in Colorado measured the difference in the flow of time between two layers of atoms separated by 1 millimeter. Not 1 kilometer, not 1 meter, 1 millimeter. The thickness of a credit card. The difference was real and measurable. The atoms at the top of the sample experienced time passing at a fractionally faster rate than the atoms at the bottom, exactly as general relativity predicts for objects at different heights in a gravitational field. The precision required to detect this was 7.6 times 10 to the power of -21. Right now, as you listen to this, time is passing slightly faster at the top of your head than at your feet. Your head is aging at a marginally different rate than your shoes. The difference over a human lifetime is too small to notice, but it is not zero. If time is that local, that sensitive to exact position, that dependent on a difference of 1 millimeter in altitude, then what is the thing we are calling time? Is there one unified phenomenon, or just a collection of local rates we have bundled under one name for convenience? And if it is the latter, if time is a useful shorthand we construct from our immediate surroundings, then what does it mean to say the universe has a history? What does it mean to say something happened before something else, if before depends on exactly where you are standing? There is something that physics has known for 130 years and has never quite figured out what to do with. Take any equation that describes how the physical world behaves. Newton's laws, Maxwell's equations, quantum mechanics, general relativity. Run them forward in time. Now run them backward. The mathematics works identically in both directions. Not approximately, not with small corrections, identically. Which means nothing in the fundamental laws of physics requires time to move in the direction you experience it moving. The universe, as far as its own equations are concerned, has no preference. Forward and backward are the same. Ludwig Boltzmann saw this in 1895, and it nearly broke him. He spent years trying to explain why we perceive a direction, past to future, cause before effect, broken eggs never reassembling, when the laws governing every particle in the universe contain no such direction at all. What he eventually concluded is that the arrow of time is not a law, it is a statistical bias. The universe started in an extremely ordered, low entropy state. From that starting point, disorder increases, not because it has to, but because there are overwhelmingly more disordered states than ordered ones, and random processes tend toward the more probable. That is the entire explanation for why time has a direction, not a fundamental law, a statistical tendency. Which raises a question Boltzmann never answered and nobody has answered since. Why did the universe begin in such an ordered state in the first place? That initial condition, that improbably tidy beginning, is doing all the work. Remove it, and the arrow of time disappears entirely. And if you sit with that long enough, it becomes genuinely unsettling. Everything you experience as the passage of time, memory, aging, causality, the sense that the past is fixed and the future is open, all of it is downstream of one unexplained coincidence at the beginning of everything. In February 2025, Andrea Rocco and Thomas Goff at the University of Surrey were studying what physicists call open quantum systems that interact with their environment. They wanted to understand why time appears to flow forward in these systems even though the underlying equations are symmetric. What they found is that even after applying standard simplifying assumptions, even after accounting for the way energy and information dissipate into the environment, the equations still behave identically whether time moves forward or backward. The mathematical object at the heart of their description, what they called the memory kernel, turned out to be symmetric in time. The arrow of time was not emerging from the physics of the system. It was simply not there. What this tells us is that the direction of time we experience is not being generated by the quantum processes underneath our reality. It is being generated by something sitting above the level of the equations. And the obvious candidate, the thing that keeps appearing in result after result, is the observer, the thing doing the looking. which raises a question that sounds almost too strange to take seriously. What if the direction of time is not a feature of the universe? What if it is a feature of what it means to be aware of the universe? That question has a physical answer, and to get to it, we need to understand something Rolf Landauer proved at IBM in 1961. He showed that erasing one bit of information, resetting a switch from 1 to 0, clearing a single memory register necessarily releases a tiny amount of heat into the environment. Not because of engineering inefficiency, not because our computers are imperfect, but because the laws of thermodynamics require it. Information is physical. Manipulating it costs energy. The minimum cost scales directly with the temperature of the surrounding environment. If the arrow of time is related to entropy, to disorder increasing, and if every act of observation, every act of recording information, every act of building a memory necessarily increases entropy, then observation is not a passive window onto reality. Observation is a thermodynamic event. It produces heat, it generates irreversibility, it creates entropy, and entropy is the only thing in physics that distinguishes the past from the future. So observation does not just register the arrow of time, it participates in producing it. Every time you remember something, every time you store information about the past, you are not just recording time, you are, in the most literal thermodynamic sense, generating it. Which raises a question that deserves more attention than it usually gets. If memory creates the arrow of time, and the arrow of time is what makes the past different from the future, then what came first? Did time produce memory, or did memory produce time? In November 2025, a team at Oxford tested exactly how far that logic goes. Vivek, Vadwa, and Natalia Aries built the most minimal clock imaginable, a microscopic system of 2 quantum dots, 2 tiny regions that a single electron can jump between. Each jump is a tick. The clock keeps time in the most basic sense possible. Then they asked a question that sounds almost too simple. How much energy does it cost to run this clock compared to how much it costs to read it, to observe it, to detect the ticks, to turn quantum events into a record? The answer was not what anyone expected. Reading the clock required up to 1 billion times more energy than running it. Not twice as much, not 10 times, 1 billion. And when they analyzed where all that energy was going, they found it was producing entropy. The act of measurement was generating irreversibility. It was creating the thermodynamic conditions that make one direction of time distinguishable from the other. When the 2 quantum dots reached the same temperature, when the system was perfectly balanced, the electron jumped forward and backward with equal probability. The clock had no direction. It was equally past and future. Time in that state had no arrow. The arrow appeared only when the measurement apparatus recorded the jumps, only when something outside the quantum system built a memory of what had happened. The direction of time in this experiment was not a property of the clock. It was a property of the act of looking at the clock. The mechanism inside that Oxford experiment is worth examining carefully. The electron sits between 2 quantum dots. It can jump left or right. At the quantum level, without any measurement happening, these jumps are symmetric. The electron has no preference. Forward and backward are indistinguishable. There is no tick, there is just motion. Now the measurement apparatus turns on. It records each jump. It builds a sequence. And that sequence has a direction. It has a before and an after. The arrow of time appears the moment the record exists. The arrow is in the record, not in the electron. The electron does not know it is being observed. It does not change its behavior because of the measurement. But the entropy, the irreversibility, the thing that makes past different from future, is generated entirely in the measurement apparatus, in the act of writing the result down, which means that if you imagine a universe with no records, no memories, no structures that retain information about previous states, that universe would have electrons jumping back and forth, energy moving around, things happening, but no arrow of time, no past, no future. Just an eternal, symmetric present. That is not science fiction. That is what the Oxford experiment implies, and it connects directly to something John Wheeler argued for decades. That information is not just a description of physical reality, that, at its deepest level, the universe is not made of matter and energy, it is made of bits, of records, of questions answered. If that is right, then time itself is a record, a memory the universe keeps of itself. In quantum mechanics, time is not treated the way space is treated. Space isn't observable. You can measure position. You can put position into the equations as something the system itself possesses. Time is not an observable. It is a parameter, a number you feed into the equation from outside, like setting a dial before you run the experiment. The Schrödinger equation treats time as something that simply flows in the background, uniform and external, untouched by anything the quantum system does, which is almost exactly what Newton said in 1687. Absolute time, flowing equably, independent of everything external. Quantum mechanics, for all its revolutionary strangeness, smuggled Newton's time back in through a side door. What this means is that every quantum experiment ever run, every result we have, every prediction we have tested was conducted inside a framework where time was assumed rather than derived. We have never measured time from inside a quantum system. We have only ever measured quantum systems from inside time. Whether those are the same thing is a question that turns out to matter enormously. In 2020, a team in Vienna decided to stop treating this as a theoretical problem and actually push on it in a laboratory. Julia Rubino's team wanted to know whether the sequence of events in a quantum system has to be fixed, whether A always comes before B if A causes B. In classical physics, causality is absolute. The order of events is written into the structure of reality. What they found is that this is not how quantum systems work. They set up a situation where a quantum particle passes through two operations, call them A and B, and the order in which it experiences them is in quantum superposition, not randomly one or the other, both simultaneously, A before B and B before A at the same time, in the same experiment, for the same particle. This was not a theoretical result, it was measured. The experiment produced outcomes that could only be explained if causal order was genuinely indefinite. Not unknown, not random, but superposed. Causality, the principle that causes precede effects, that the past shapes the future and not the other way around, is not a fundamental feature of quantum reality. It is something that emerges at larger scales, the way temperature emerges from the motion of molecules underneath it. At the quantum level, before and after are not fixed. The universe does not have a built-in before. It has a before only when something forces the order to become definite. And that something keeps pointing toward the same place, toward the observer, toward the record, toward whatever is doing the measuring. When you place general relativity and quantum mechanics side by side and look at what they say about time, they contradict each other so completely that they cannot both be right about what time fundamentally is. In general relativity, time is dynamic. It is a physical dimension, a real thing that curves in response to mass and energy, that stretches near massive objects, that is woven into the geometry of the universe. It is not a background, it is a participant. In quantum mechanics, time is a fixed external parameter. It does not curve, it does not respond to the quantum system, it just flows in the background, providing the stage on which quantum events occur. These descriptions are not just different, they are structurally incompatible. General relativity needs time to be a dynamic physical thing. Quantum mechanics needs time to be an inert, external given. You cannot have both simultaneously, which means one of the two most successful theories in the history of science has an incomplete picture of something as basic as time. In 1967, John Wheeler and Bryce DeWitt tried to do the obvious thing. Write down the quantum mechanics of the universe as a whole, not the quantum mechanics of a particle or an atom, the universe, all of it, one equation. When you attempt this, you immediately run into a technical problem. General relativity describes how the geometry of space-time evolves over time. Quantum mechanics describes how quantum states evolve over time. To combine them, you need a single equation that handles both. When Wheeler and DeWitt wrote that equation, time disappeared. Not approximately, not in some limiting case. The time variable, the t that appears in every other equation in physics, was simply absent from the final result. The universe as a whole, described by the most complete equation physicists could construct, does not evolve in time, it just is, static, timeless, a single quantum state with no before and no after. This is called the Wheeler-DeWitt equation, and it is not a fringe result. It is the starting point for every serious attempt at quantum gravity, and what it says, with complete mathematical clarity, is that time is not a fundamental feature of the universe. It is something that has to emerge somehow from a timeless underlying reality. The question is how? How do you get time from a universe that the equations say has none? In 2013, one team decided to stop debating this and test one of the candidate answers in a laboratory. The result is one of the most quietly unsettling findings in modern physics. and it almost never comes up outside specialist discussions. Ekaterina Moreva and her colleagues built a simple quantum system: two entangled photons. One acted as the clock, the other acted as the observer. Then they looked at the system in two different ways. First, from the outside, treating the whole two-photon system as a single object and measuring it from without. From this perspective, the system appeared static, timeless, no evolution, no change, no before or after. Exactly what the Wheeler-DeWitt equation predicts. Then they looked from the inside, using one photon to measure the other, letting the internal observer track the internal clock. From this perspective, time existed. The clock ticked, events had a sequence. The internal observer experienced time passing. Same system, same physical setup. Two completely different realities depending on where you stood. If you were outside, the universe had no time. If you were inside, it did. What this means is almost too large to hold in one thought. Time may not be a property of the universe. It may be a property of being inside the universe. It may be what it feels like to be part of something rather than a spectator of the whole. And if that is true, then every question we thought we knew how to ask about the beginning of time, the end of time, the direction of time, all of them need to be reframed entirely. Not because the questions are wrong, but because the thing they are asking about is not where we thought it was. There is a further implication of the Moreva experiment that most summaries miss. If you are inside a system, you experience time. If you are outside, you do not. And the universe, by definition, has no outside. There is no position you can occupy that is not inside it, which means the timeless description, the Wheeler-DeWitt equation, the static quantum state, the universe with no before and no after, is a description from a perspective that physically cannot exist. No observer can ever stand there. The only description any real observer can ever access is the internal one, the one where time exists. This does not mean time is an illusion. It means something more precise. Time is real, but only locally, only from inside, only for participants. The universe does not have a single time everyone shares. It has a collection of local times, each one arising from the relationship between a particular observer and a particular clock. What we call time, the thing we measure, feel, and structure our entire existence around, is something that emerges from entanglement, from quantum correlations between parts of a system that has no global time at all. While theorists worked through what the Moreva result meant, other physicists were doing something more immediate. They were pushing on general relativity with a precision it has never faced before, looking for the exact point where it starts to show a crack. The ACES mission, the Atomic Clock Ensemble in Space, is currently running on the International Space Station. It carries two clocks: Pajaro, a cold atom cesium clock developed by a French space agency, and a hydrogen maser built by Swiss institutions. Together, they generate a time signal with a fractional frequency stability of 1 × 10⁻⁻16. At that level of precision, even the smallest deviations from general relativity's predictions become visible. What the mission is looking for is any departure from what Einstein's equations predict for how time runs at that altitude and velocity, not to confirm relativity. Relativity has been confirmed enough times. What they are looking for is where it fails, because everyone in the field knows it must fail somewhere. General relativity and quantum mechanics cannot both be completely correct, and at some level of precision, one of them has to show a crack. ACES is sensitive enough that if the crack exists at the scale physicists expect, it should appear in the data. The results are still coming in, and we are living at the exact moment when the most precise test of time ever conducted is running, and the answer is not yet in. What ACES cannot do is test general relativity and quantum mechanics simultaneously in a single measurement. Those two theories live at different scales, and every experiment before now has tested one or the other, never both at once. That changed in July 2025. Igor Pekovsky at Stevens Institute, Jacob Covey at the University of Illinois, and Johannes Beauregard at Harvard published a protocol that does something almost audacious in its ambition. Their design puts an atomic clock into a superposition of two different heights above Earth's surface. The same clock at the same moment is simultaneously higher and lower. In quantum mechanics, both are real. In general relativity, the two heights correspond to two different rates of time flow, so the clock in superposition is simultaneously experiencing two different rates of time. The interference between those two time flows, the quantum signature of the superposition, can be measured. This has never been done before because it requires both quantum coherence and gravitational precision at a level that only recently became technically feasible. Every experiment before this tested quantum mechanics in flat, space-time, or general relativity without quantum effects. This is the first protocol that makes both theories show up in the same number at the same moment. And if that number does not match what either theory predicts individually, if the combined quantum gravitational behavior of time is something neither framework anticipated, then we will have direct experimental evidence that both are approximations to something we do not yet have. A theory without a name, a theory nobody has written down yet. There is a detail about quantum transitions that does not fit comfortably into any of the frameworks we have been building. In February 2026, Hugo Dill's team at EPFL measured how long it takes an electron to absorb a photon and jump to a higher energy state without using any external reference clock. Every previous measurement of this kind relied on a clock sitting outside the quantum system, timing it from without. What Dill's team did instead was use the quantum system's own internal structure to record the duration. When an electron absorbs a photon, it can follow multiple quantum pathways simultaneously. These pathways interfere with each other, and the interference leaves a signature in the spin of the emitted electron. By analyzing that signature, the team could determine how long the transition took, entirely from information encoded inside the process itself. What they found is that quantum transitions are not instantaneous. They have a measurable duration, but the duration depends on the atomic structure of the material. Change the symmetry of the crystal, and the transition takes longer. Lower symmetry, longer time. Higher symmetry, shorter time. The geometry of the material determines how long the quantum event lasts. Not an external clock, not the flow of time in the background, the shape of the thing itself. If the duration of a quantum event is determined by internal geometry rather than external time, what exactly is flowing when we say time flows? Is it possible that what we call time is just a way of describing the internal geometry of processes? That duration is not something events happen inside, but something that is a property of the events themselves. And back to that NIST clock from the beginning. The aluminum iron clock, accurate to the 19th decimal place, 41% more precise than anything before it, is now sensitive enough to detect changes in the fundamental constants of nature. The fine structure constant, which determines how strongly electrons interact with light, the gravitational constant, which sets the strength of gravity. These numbers appear throughout physics as fixed values written into the equations as given, but they are not derived from anything deeper. They are measured, and if they are measured quantities rather than mathematical necessities, there is no fundamental reason they have to stay constant. They could drift slowly, almost beyond detection, but measurably, if you have a precise enough instrument. The NIST clock is now precise enough to check, not assume, actually check. If the constants are drifting, if the fine structure constant today is not exactly what it was a billion years ago, then the laws of physics as we know them are not eternal truths. They are snapshots, descriptions of the universe as it happens to be right now, at this moment in cosmic history. And if the laws are changing, then time, the dimension along which they change, is more fundamental than the laws themselves. Time stops being a consequence of physics and becomes the thing physics happens inside. That inversion connects directly to a crack that has been widening at the center of cosmology for about a decade. There is a number that should be singular and is not. It is the Hubble constant, the rate at which the universe is expanding. When physicists measure it two independent ways, they get two different answers. The first method uses the cosmic microwave background, the faint afterglow of the early universe, mapped with extraordinary precision by the Planck satellite in 2018. This gives 67.4 km per second per megaparsec. The second method uses Cepheid variable stars as distance markers and gives 73.2 km per second per megaparsec. The difference is 5 sigma. In physics, 5 sigma is the threshold for calling something a discovery. This gap is large enough that it almost certainly cannot be explained by measurement error. Both teams have checked their work repeatedly. The numbers do not converge. The Hubble constant is not just a rate of expansion. It is a rate of change in the geometry of space-time itself. It tells you how fast the fabric of the universe, including the time dimension, is evolving at cosmic scales. If two independent methods of measuring that rate disagree by 5 sigma, it means we do not fully understand how the geometry of space-time is behaving on the largest scales. And if we do not understand that, Our entire picture of cosmic time, the 13.8 billion year timeline, the sequence of cosmic events, the age of structures, is built on something that is not fully resolved. Then in 2024, the situation got worse. The Dark Energy Spectroscopic Instrument spent years mapping the distribution of galaxies across enormous volumes of the universe, using the patterns of that distribution to measure how cosmic expansion has changed over time. What it found is that dark energy, the force driving the acceleration of expansion, the thing Einstein called the cosmological constant, may not be constant at all. The data suggests it is weakening, slowly but measurably. It was stronger in the early universe and has been decreasing since. Dark energy is the engine driving the expansion of space, and the expansion of space is the mechanism by which the universe has a cosmic history, a sequence of events, an earlier and a later. If the engine is not constant, then the rate at which cosmic time flows is not constant either. The universe is not just expanding, it is expanding at a rate that is itself changing in a way we did not predict and do not fully understand. There is an older result that grounds all of this in something more tangible than cosmological measurements. In 1959, Robert Pound and Glenn Rebka did an experiment at Harvard that is about as clean and direct as physics gets. They measured whether light changes frequency as it moves through a gravitational field. They did this by shining gamma rays up a tower 22.5 meters tall and measuring whether the frequency of the light at the top differed from what was emitted at the bottom. It did. The shift matched exactly what general relativity had predicted, a prediction Einstein had made in 1907, 52 years before anyone measured it. Time really does run slower at the bottom of a tower than at the top. Not by much, a few parts in 10 to the power of 15, but unambiguously, repeatedly, in a building in Cambridge, Massachusetts. The strangeness is not at the edge of physics, it was in that building in 1959. We just did not fully see it yet. Something physicists had been predicting for decades, but had never managed to produce cleanly in a laboratory, finally happened in December 2025. Hadiseh Moussa and his team at the City University of New York built a system that reflects electromagnetic waves in time rather than in space. Normally, when a wave hits a boundary, a wall, a surface, a transition between two materials, it reflects back through space. Moussa's experiment created a temporal boundary instead. By suddenly and uniformly changing the physical properties of the medium the wave was traveling through, shifting the electrical permittivity of the system instantaneously, they created a moment in time where the wave experienced a discontinuity, and the wave reflected, not backward through space, backward through time. The signal began retracing its own history. It went back through the same medium it had already passed through, reproducing the past states of the wave in reverse order. The team also observed frequency translation. The reflected wave emerged at a different frequency than the original, which is the temporal equivalent of a wave changing direction when it enters a different medium. The result was clean, repeatable, and confirmed a theoretical prediction that had existed since the 1960s without ever being clearly demonstrated. The experimenters are careful to note that time outside the system continued normally. What changed was the behavior of the wave inside an engineered temporal boundary. If the boundary between past and future is something that can be engineered, something that responds to the physical properties of a medium, what exactly is that boundary? What is it separating? The mechanism reveals something about time that was always true and had simply never been demonstrated this clearly before. When a wave hits a spatial boundary, what is conserved is its frequency. The pitch stays the same, the direction changes. The temporal boundary works the opposite way. What is conserved is the direction. The wave keeps moving forward through space, but its frequency shifts, and simultaneously, a time-reversed copy of the wave is generated. This follows from Maxwell's equations, which are among the most tested relationships in all of physics, which means the capacity for time reversal is not something exotic. It is already there, in the structure of the equations, waiting for the right physical conditions. The asymmetry of time, the fact that signals propagate into the future and not the past, is not written into the laws of electromagnetism at all. It is written into the initial conditions. In 2012, the Babar experiment at SLAC measured direct evidence of time reversal violation in subatomic particles. They were studying B mesons, unstable particles that can transform into their antiparticle equivalents. The question was whether the process of going from state A to state B was statistically identical to the process of going from state B back to state A. If time is truly symmetric, those rates should be equal. They were not. The transition rates differed by a measurable amount. Then, in 2020, the T2K experiment in Japan found a related asymmetry in neutrinos, matter, and antimatter versions of the same particle, oscillating between different types at different rates. Both results are real, both are statistically robust, and both show that the arrow of time is not just a statistical tendency at large scales, the way Boltzmann described it. It is built into the behavior of individual particles in ways that the standard model can accommodate mathematically, but cannot explain from first principles. We can describe the asymmetry. We cannot say why it exists. There is a result from quantum mechanics that adds something almost opposite to this picture. Not that time has a forced direction, but that observation can stop it entirely. It is called the quantum Zeno effect, first proposed by George Sudarshan and B.N. Misra in 1977 and confirmed experimentally multiple times since. A quantum system evolves over time. A particle decays, an atom transitions between energy levels, a quantum state changes. This evolution has a characteristic timescale. But if you measure the system frequently enough, if you observe it fast enough, the evolution slows down. The more often you look, the slower it changes. And in the limit of continuous observation, the system stops evolving entirely. It freezes. You can hold a quantum system in its current state indefinitely simply by measuring it fast enough. Put this alongside the Oxford experiment. Observation creates the arrow of time. The Zeno effect says, observation also controls the rate of time, how fast quantum evolution proceeds. Frequent observation slows quantum time. No observation removes the arrow entirely. And the act of observing costs energy, as Landauer showed, which means that controlling time at the quantum level has a thermodynamic price. You pay to slow it. You pay to give it direction. Time, in this picture, is not a river flowing independently of everything around it. It is something closer to a process that requires participation to sustain and participation to direct. If observation sustains time, if the rate and direction of time depend on the presence and frequency of measurement, what was time doing before there was anything in the universe capable of observing anything? Was it doing anything at all? In 2024 and 2025, multiple teams at the Physikalische Technische Bundesanstalt in Braunschweig and at Gela in Boulder demonstrated working nuclear clocks based on thorium-229. The difference between these and conventional atomic clocks is not just precision. It is what is doing the oscillating. Atomic clocks use the transitions of electrons in the outer shells of atoms, which interact with the surrounding electromagnetic environment. Nuclear clocks use transitions inside the atomic nucleus itself, shielded from almost everything outside by the electron cloud surrounding it. The result is a stability orders of magnitude better than atomic clocks and a sensitivity to effects that atomic clocks cannot reach, specifically to changes in the strong nuclear force, the force holding protons and neutrons together. If the strong force has a coupling constant that varies even slightly over cosmological time, a nuclear clock will eventually detect it. If fundamental constants are changing, then the laws of physics are historical rather than eternal. They have a before and an after, which means they are inside time. And if the laws are inside time, time cannot be derived from the laws. Something has gone in a circle. In physics, a circle usually means a missing piece. The nuclear clock is the first instrument precise enough to start looking for it. The international community is also preparing to redefine the second. A coordinated comparison of optical clocks across 6 countries, published in June 2025, was a major step toward making this formal sometime around 2030. The current definition, based on cesium oscillation since 1967, is being replaced with something based on optical transitions, oscillating at frequencies roughly 10,000 times higher than cesium. The redefinition is not just a technical upgrade. It is an admission that the previous ruler was not precise enough to measure the thing we are actually trying to understand. Every definition of the second, the old one and the new one, is a definition of how time behaves, not what time is. The new ruler will be precise enough to show us things we have never seen before. Whether what it shows us will tell us what time actually is, or just give us more precise descriptions of something we still do not understand, that is the question the redefinition process deliberately avoids. The twin paradox, The thought experiment where one twin travels at high speed and returns younger is not actually a thought experiment. It has been measured. Astronauts who spend 6 months on the International Space Station return to Earth having aged approximately 0.007 seconds less than people who stayed on the ground. Scott Kelly, who spent nearly a year on the ISS, is measurably younger than his identical twin Mark, who remained on Earth. The difference is 7 milliseconds over 340 days. Real. Measured, which means two people who were born at the same moment, who started with identical clocks, lived different amounts of time during the same historical period. They experienced different quantities of duration. When Scott Kelly returned from the ISS, he and his brother were not at the same moment in time in any absolute sense. They were at the same location in space, but the amount of time each had passed through was different. Their nows were not the same now. And if that is true for two people separated by 400 kilometers of altitude and orbital velocity, it is true in principle for any two objects anywhere in the universe. Every object carries its own local time. Those local times do not sum to a single shared timeline that the universe is moving through together. There is no universal now. Einstein showed in 1905 that two events simultaneous for one observer are not simultaneous for an observer moving relative to the first. This is not an illusion caused by signal delays or imperfect clocks. It is a genuine feature of the geometry of space-time. The events really do occur at the same time in one reference frame and at different times in another. Neither frame is more correct. Both are equally valid descriptions of reality. The concept of now, a single present moment extending across space, is not a feature of the universe. It is a feature of a particular reference frame. Change your velocity and your now changes. The physicist Reed Dyke and the philosopher Putnam argued in the 1960s that this implies a block universe, a four-dimensional structure in which all moments of time exist equally, past, present, and future all equally real, with the experience of flow being a perspective effect rather than a fundamental feature of reality. David Albert has pushed back on this, arguing that the block universe interpretation smuggles in assumptions about what real means that the physics does not force. Both positions are still actively debated. What is not debated is the underlying physical fact. The present moment, as you experience it, is a local phenomenon. Carlo Rovelli concludes from all of this that time is not a river. A river has banks, a current, a direction that exists independently of the water. Time is more like heat. Heat does not exist in a single molecule. It is not a property of any individual particle. It emerges from the collective behavior of enormous numbers of particles interacting, and it flows from hot to cold, not because any law demands it, but because the statistics of large numbers overwhelmingly favor it. Remove the large numbers, go down to individual interactions, and heat loses its meaning entirely. Time, Rovelli argues, works the same way. At the level of fundamental physics, in the equations describing individual quantum events and their relations, there is no time, no flow, no direction, no before and after. These emerge only when you zoom out, when you have enough interacting parts, enough entanglement, enough thermodynamic complexity that statistical behavior kicks in and entropy starts to increase. Time is what the universe looks like from the inside, when it is big enough and complex enough to have a thermodynamic arrow. Lee Smolin looks at the same data and arrives at almost the opposite conclusion. His argument starts with a question Rovelli's framework leaves unresolved. If the laws of physics are what they are because of what they are, if the constants and equations are fixed, given from outside, not derived from anything deeper, then the universe requires an explanation that physics cannot provide. Where do the laws come from? Why these values and not others? Smolin's proposal is that the laws evolved, that the universe has a history not just of events but of physical law itself, that the parameters of physics have changed over cosmic time, selected by something like natural selection acting on universes. Each black hole that forms might spawn a new universe with slightly different constants. Universes that produce more black holes reproduce more. The laws we live under are the laws that survived. If the laws evolve, then time is prior to the laws. You cannot derive time from the laws if the laws are themselves products of time. Time has to be the one thing that does not emerge from anything else. Everything else, including the rules, emerges from it. This puts Smolin in direct opposition to Rovelli. One says time is emergent, the other says time is fundamental. Both are using the same experimental results as their starting point. The fact that two serious physicists who have spent their careers on exactly this question can sit with identical evidence and reach incompatible positions is, I think, the most honest summary of where the field actually stands. David Albert's contribution to this picture is quieter than Ravelli's or Smolin's, but cuts just as deep. His argument identifies what he calls the past hypothesis, the single assumption that does all the work in our experience of time. The assumption is this: the universe began in a state of extraordinarily low entropy, and from that starting point, entropy has been increasing ever since. Not because any law requires it, as Boltzmann showed, but because there are overwhelmingly more high entropy states than low entropy ones, and random processes move toward the more probable. That is the entire explanation for why you remember the past and not the future. Why causes precede effects, why broken things do not spontaneously reassemble, why time feels like it has a direction. All of it is downstream of one fact. The beginning was very ordered. Remove that one fact, keep everything else identical, and the arrow of time disappears. Past and future become indistinguishable. Memory becomes meaningless. Causality collapses. Everything that makes time feel like time depends on that single initial condition. And that initial condition is not derived from any deeper principle. It is an assumption we make because the evidence is consistent with it, not because any theory predicts it. Which means every experience you have ever had, every memory, every plan, every sense that there was a yesterday and there will be a tomorrow is not grounded in a law of nature. It is grounded in a statistical accident at the beginning of everything. Why was the beginning so ordered? What selected that initial condition out of the vast space of possible initial conditions? Roger Penrose offers an answer through conformal cyclic cosmology. The arrow of time points from low entropy to high entropy. But why was entropy so low at the beginning? Why did the universe start in extraordinary order when the overwhelming majority of possible initial states are disordered? Penrose refuses to accept that the answer is simply that it did. His proposal is that the Big Bang was not a beginning, it was a transition. In conformal cyclic cosmology, the universe passes through an infinite sequence of eons. Each eon starts with something like a Big Bang and ends with something like a heat death. But in the far future of an eon, when all matter has decayed and all black holes have evaporated, only massless particles remain, photons and gravitons moving at the speed of light. And massless particles do not experience time, they have no internal clock. The distinction between a nanosecond and a trillion years does not exist for them. At that point, Penrose argues, the universe loses track of scale. It cannot distinguish between very large and very small. In that scaleless state, the cold empty end of one eon and the hot dense beginning of the next become geometrically equivalent. The heat death and the Big Bang are the same moment seen from different sides. The end of time and the beginning of time are the same event, which means the low entropy beginning of our universe is not an accident requiring explanation. It is a mathematical consequence of the high entropy end of the previous one. Stephen Hawking arrived at a similar dissolution from a completely different mathematical direction. Working with James Hartle in 1983, he proposed the no-boundary condition, a way of describing the quantum state of the universe that does not require an initial condition at all. The approach uses a technique called a Wick rotation, which replaces real time with imaginary time, multiplying the time coordinate by the square root of -1. In imaginary time, the distinction between time and space disappears. The 4 dimensions of space-time become 4 spatial dimensions, all equivalent, none playing the special role time plays in ordinary physics. And in this 4-dimensional spatial geometry, there is no boundary, no edge, no point you can call the beginning. Just as the surface of the Earth has no edge and you can travel in any direction indefinitely without reaching a wall, the universe in imaginary time has no beginning. The Big Bang, when you rotate back from imaginary time to real time, appears not as a moment where time starts from zero, but as the point where a spatial geometry transitions into a space-time geometry. A smooth, rounded cap. Time did not begin there. It emerged there from a region where the distinction between time and space did not yet apply. Both Penrose and Hawking are pointing at the same thing from opposite directions. Penrose says the beginning was the end of something else. Hawking says the beginning was a smooth, geometric transition from a timeless state. Both dissolve the question of what came before, but neither answers the question that emerges from dissolving it. If time emerged, whether from a previous eon or from imaginary geometry, what determined which way it would point when it appeared? There is one piece of this picture that connects the largest scales to the smallest in a way none of the theoretical frameworks have managed to reconcile. It concerns black holes and what happens to information inside them. Hawking showed in the 1970s that black holes emit radiation, now called Hawking radiation, as a consequence of quantum effects near the event horizon. This radiation is thermal. It carries energy, but no information about what fell into the black hole. And as the black hole slowly evaporates, the information about everything that ever fell in, every particle, every quantum state, every bit of physical data appears to be gone, not hidden, not encoded in correlations too subtle to detect, gone. This violates unitarity, the requirement in quantum mechanics that quantum evolution is reversible and that information is always conserved. To say that the past is definite, that events happened in a specific sequence, is to say that information about those events is preserved somewhere in the present. If black holes destroy information, they destroy the definiteness of the past. They introduce a genuine ambiguity into the timeline of the universe that no experiment from outside can resolve. And there are a lot of black holes, which means the past may be less definite than we assume. And if the past is not fully definite, if the timeline of the universe has genuine gaps in it, then what exactly is the thing we are trying to measure when we point a clock at reality? John Wheeler spent decades pushing a single idea that most of his colleagues found too strange to engage with seriously, and that the experiments of the last decade have made increasingly difficult to ignore. He called it from bit. The idea is that information is not a description of physical reality, it is what physical reality is made of. That every particle, every field, every physical quantity derives its existence from answers to yes or no questions, from binary choices, from bits. The universe is not a collection of things that can be described with information. It is a collection of information that we interpret as things. If information is fundamental, if the universe is at its deepest level, built from answers to questions, then the question of who or what is doing the asking is not a side issue, it is the central issue. A bit is not a bit in the absence of something that distinguishes between the two states. A yes or no question requires something that can ask it, which means Wheeler's framework does not just describe physics, it makes the existence of observers a necessary feature of reality rather than an accidental one. And if observation is what generates the arrow of time, as the Oxford experiment showed, if the direction of time is a product of the act of measurement, of the creation of records, of the thermodynamic cost of looking, then the observer is not just a witness to time, the observer is part of what produces it. This is not mysticism, it follows from the mathematics of quantum mechanics and from the experimental results of 2013 and 2025 taken together. The Morava experiment showed that time exists only for internal observers. The Oxford experiment showed that the arrow of time emerges from the act of observation. Wheeler's framework gives these results a coherent interpretation. The universe, at its deepest level, is timeless. Time is what it looks like from inside when something is doing the looking. Wheeler himself asked the question in its sharpest form near the end of his life. Did the universe require observers in order to have a past? Not just a future, a past. His delayed choice experiment suggested that the act of observation can, in a precise quantum mechanical sense, reach backward and determine how a particle behaved at an earlier moment. The past in those experiments is not fixed until something in the present forces it to be fixed, which means the past might not be a record of what happened. It might be a construction assembled backward from the present, shaped by every act of observation that has ever occurred. And if that is true, then asking what time is may be inseparable from asking what memory is, from asking what it means to know that something happened, from asking whether the difference between the past and the future is a feature of reality or a feature of minds embedded in reality. Here is where we actually are, not where the textbooks say we are. We have built the most accurate clocks in the history of measurement, and they are telling us the constants of nature may not be constant. We have run experiments showing the arrow of time is not in the laws of physics, but in the act of observation. We have a mathematical description of the entire universe that contains no time variable. We have laboratory evidence that causality is not absolute, that quantum transitions have durations determined by geometry rather than the flow of time, and that time can be reflected at an engineered temporal boundary. We have two independent measurements of the expansion rate of the universe disagreeing by 5 sigma, We have a theoretical picture in which time emerges from thermodynamic complexity, and a competing picture in which time is the only fundamental thing, and both are consistent with the available data. And we have an unsolved problem at the center of all of it. Why did the universe begin in such an ordered state that none of the frameworks can answer? What we do not have is a clear, consistent, experimentally confirmed account of what time is. And I want to sit with that for a moment rather than move past it too quickly, because there is a way of hearing that sentence that makes it sound like a temporary situation. A gap in knowledge that will be closed by the next generation of experiments, the next theoretical breakthrough, the next decade of data from ACEs or the nuclear clocks, and maybe it will be. But the deeper the experiments go, the more the question ramifies rather than converging. Every result that was supposed to clarify the nature of time has produced a new version of the puzzle. The more precisely we measure, the more precisely we can see that we do not understand what we are measuring. The question of what time is has turned out to be the same question as what an observer is, what information is, what the past is, what it means for something to exist rather than not exist. These are not separate questions that happen to be related. They seem to be the same question approached from different directions. And if that is right, then the answer to what time is will not come from a better clock or a more precise measurement alone. It will require a new way of thinking about what physical reality is at the level where time, information, and observation meet. We do not have that yet. We have pieces of it scattered across 100 years of experiment and theory, pointing in roughly the same direction without quite connecting. What I do know is that every experiment running right now, ACEs on the space station, the nuclear clocks in Braunschweig and Boulder, the quantum network protocols being built in laboratories across 3 continents, is probing the same boundary from a different angle. The answer, if there is one, is somewhere in the data being collected right now, or it is somewhere in the data that will force us to ask a question we have not thought to ask yet. If you found this exploration of the physics of time as fascinating as the physicists who are still working through it, take a moment to like this video. It helps more people find their way to conversations like this one. The questions we have been sitting with tonight are genuinely open. The clocks are running, the numbers still do not add up. And somewhere in the gap between what the measurements show and what the theories predict, the actual nature of time is waiting. Whether we are close to finding it or just beginning to understand how deep the search goes, that remains one of the most honest and most difficult open questions in all of science. There is a dimension of this that rarely gets discussed in popular treatments of time, but which sits directly at the intersection of every experiment we have covered. It concerns the relationship between time and thermodynamic complexity, and it is worth pursuing carefully because it changes what the experiments mean. When Boltzmann identified entropy as the source of time's direction, he was making a statistical argument. The universe moves from order to disorder because there are more disordered states than ordered ones. But there is something deeper embedded in that observation that took over a century to fully appreciate. Entropy is not just a measure of disorder, it is a measure of missing information. The entropy of a system is, in a precise mathematical sense, the number of bits of information you would need to fully specify the microscopic state of that system, given what you already know about it from macroscopic observation. A high entropy system is one about which you know very little at the microscopic level. A low entropy system is one whose microscopic state is highly constrained by what you can observe at the macroscopic level. This connection between entropy and information was formalized by Claude Shannon in 1948 in work that was nominally about the mathematics of communication but turned out to be about the deep structure of physical reality. Shannon's entropy formula is mathematically identical to Boltzmann's. They are measuring the same thing from different angles, and what this identity tells us is that the arrow of time, the increase of entropy, is simultaneously an increase in the information content of the universe and a decrease in the precision with which the past can be reconstructed from the present. As time passes, in the direction we experience it, the universe becomes harder to read backwards. More information is required to specify where things came from. The past becomes, in a precise quantitative sense, more inaccessible. The future is open because it has not yet generated the information needed to specify it. The past feels fixed and certain because we carry records of it, but those records are always incomplete, always losing detail, always requiring more and more information to reconstruct accurately. And in the limit, for any system that has undergone enough thermodynamic evolution, the past becomes formally unrecoverable. Not just difficult to access, provably Mathematically unrecoverable, the Landauer connection now takes on a sharper meaning. Every time you build a memory, every time you record an event, you are spending entropy to push the boundary of this unrecoverability forward in time. You are making a local exception to the general drift toward inaccessibility. Memory is the act of resistance against the thermodynamic erasure of the past, and that resistance has a cost, Landauer's limit. The minimum amount of heat you must dissipate to maintain a record. This is why the brain generates heat, not just because neurons fire, but because every thought, every memory consolidation, every act of storing information about the past is a thermodynamic transaction with the universe. You are paying, in entropy, for the privilege of having a past at all. What the Oxford experiment revealed is that this is not just a practical limitation, it is a foundational one. Without that thermodynamic transaction, without the heat generated by the act of measurement, there is no arrow. There is no before or after. There is only the symmetric quantum dance, equally probable in both directions, with no preferred direction and no accumulated record. The arrow of time is the wake left by the thermodynamic cost of knowing. This connects to something else that has been quietly transforming the field since roughly 2015, the relationship between quantum entanglement and the emergence of space-time. The work of Mark van Ramsdonk at the University of British Columbia began with an observation that sounds almost poetic but has real mathematical content. Two quantum systems that are maximally entangled, each containing complete information about the other, can be thought of as a single unified system viewed from the outside. Two systems that share no entanglement are completely separate, with no connections between them. And two systems that share intermediate levels of entanglement are connected, but through a space with some geometry, some distance, some structure. Increase the entanglement and the two systems are effectively closer together. Decrease it and they drift apart. Decrease it to zero and they become disconnected, separate universes with no way to communicate. What Van Ramsdonk's work suggests, and what subsequent work in the program called it From Qubit has elaborated, is that the geometry of space, the spatial fabric within which events have locations and distances, may itself be a product of entanglement. That space is what entanglement looks like when you view it from the inside. If that is right, then time, as the fourth coordinate of space-time, may also be a product of entanglement, not a background in which entanglement occurs. A product of the entanglement itself. Space-time is not the stage on which quantum systems perform. Space-time is what the performance looks like when you are inside it. This is related to, but distinct from, what the Morava experiment demonstrated. Morava showed that time exists for internal observers within a quantum system and not for external ones. The IT from Qubit program is suggesting something more radical. That the geometry of the space in which observers find themselves embedded is itself constructed from the entanglement structure of the quantum systems they are made of. You do not need a pre-existing space-time for quantum systems to live in. The space-time emerges from the quantum systems, and the time dimension of that space-time emerges from the same quantum correlations as the spatial dimensions, just shaped differently, just oriented differently relative to the causal structure of what is going on. This connects the Morava result to the Wheeler-DeWitt equation in a way that was not fully visible before. The Wheeler-DeWitt equation says the universe as a whole has no time. The IT from Qubit program says space-time, including time, emerges from entanglement. The Morava experiment shows that time exists for internal observers in an entangled quantum system. Put these together and a picture starts to form. The universe has no time globally. It has time locally, wherever entanglement creates structure, wherever internal correlations generate the appearance of before and after for the systems embedded in those correlations. Time is not the river that everything flows through. Time is the current that entanglement generates when there is enough complexity to generate it. There is a concept in this territory called the Page-Wouters mechanism, named after Don Page and William Wouters, who first proposed it in 1983, 30 years before the Morava experiment tested it. The mechanism works like this. If the universe is in a timeless quantum state, as the Wheeler-DeWitt equation says, then time can still emerge for subsystems within it. Specifically, it emerges from the entanglement between a clock subsystem and the rest of the universe. The clock does not tick against an external time background. It ticks relative to the other quantum systems it is entangled with. The passage of time is the change in that entanglement, not the change of anything against an external standard. Page and Wouters were largely ignored for 3 decades. The machinery was not available to test their idea, and it seemed too speculative to take seriously without a test. Then Moreva's team built it, and the mechanism worked exactly as predicted. The internal observer saw time. The external observer saw nothing. The entanglement between clock and observer was the source of the temporal experience, not a background time in which the entanglement occurred, which means that when we ask what time is, we are in part asking what entanglement is. And what entanglement is a form of information, a form of correlation between quantum states that cannot be factored out, cannot be reduced to classical correlations, cannot be explained without acknowledging that the two systems share a history, a joint quantum state, a non-local connection that persists regardless of spatial separation. Time is what entanglement feels like from the inside. This is a strange sentence to write and a stranger one to sit with, but it is, given what the experiments now show, not obviously wrong. And in physics, not obviously wrong is a meaningful category. The nuclear clock results from 2024 and 2025 add another layer to this. Nuclear clocks based on thorium-229 oscillate at optical frequencies using a transition in the atomic nucleus itself. The energy gap involved in this transition is extraordinarily sensitive to the value of certain fundamental constants, particularly the ratio of the electromagnetic force to the strong nuclear force. If that ratio changes, the frequency of the clock changes. By monitoring the frequency with extreme precision over years and comparing it to other clocks based on different physical principles, you can detect drift in the underlying constants at a level of precision that was simply not available before. What makes this experiment important, beyond its obvious precision, is what it is looking for. The fine structure constant, which sets the strength of electromagnetic interactions, appears in almost every equation of physics. It is the number that determines how atoms form, how light is emitted and absorbed, how chemical bonds work, how biological systems function. If it has been drifting, slowly, over cosmological timescales, then the physics of the early universe was genuinely different from the physics of today. Not just different in structure, different in the fundamental values that determine what is possible. Atoms that exist today might not have existed at the same temperatures and densities under slightly different constants. Chemistry that emerged in our epoch might not have emerged in a slightly different one. The pathway from the Big Bang to complex structures to life to whatever is doing this measuring might have been made possible by exactly the value the fine structure constant has right now. Not a lower value, not a higher value. This one, in this epoch, which is when we are here to measure it. That cannot be dismissed as a coincidence, but it also cannot be explained. Not yet. Not with any theory currently in hand. There is a class of theoretical framework that attempts to address this. It is called the landscape of string theory, and it proposes that the constants of nature are not uniquely determined by any deeper law. They are instead selected from an enormous space of possible values by some combination of anthropic reasoning and historical contingency. In different regions of the multiverse, if the multiverse exists, different values of the constants prevail. We observe the values we observe because those are the values compatible with the existence of observers. But this framework, whatever its theoretical merits, is not currently falsifiable in any direct sense. You cannot run an experiment that distinguishes between a universe where the constants were selected anthropically and a universe where they are what they are for dynamical reasons we do not yet understand. Nuclear clocks are the first instruments that can tell us whether the constants are stable or not. Whatever they find, the finding will constrain what the possible explanations can be. The connection between all of this and the Hubble tension is closer than it might appear. The Hubble tension, the disagreement between the two independent measurements of how fast the universe is expanding, is not just a cosmological puzzle, it is a puzzle about time. The Hubble constant does not just describe how fast galaxies are flying apart. It describes how fast the temporal dimension of space-time is evolving at cosmic scales. The age of the universe, 13.8 billion years, is derived directly from the Hubble constant. But 13.8 billion years is calculated using the value derived from the cosmic microwave background method. If the value from the Cepheid method is correct, the age comes out differently. The timeline shifts. Events we thought we had dated to certain epochs may have occurred at different moments. The entire framework of cosmic history, within which we situate the formation of galaxies, stars, planets, and the conditions for complex chemistry, rests on the value of the Hubble constant. And we have two measurements of it that disagree by enough that both cannot be right. There are several proposed explanations. Some involve new physics beyond the standard model, early dark energy that was present in the universe before recombination and has since diluted, changing the ruler against which cosmic distances are measured. Some involve modifications to general relativity at large scales. Some involve unknown systematic errors in one or both measurements. None of them has achieved consensus, and the significance of the disagreement has not decreased as more data has accumulated. If anything, it has become more robust, which means the tension is almost certainly telling us something real, something we are missing about the physics of the expanding universe, something that touches the relationship between space, time, and whatever is driving the acceleration of expansion. The DESI result, showing that dark energy may itself be evolving, fits into this picture in a way that is concerning rather than reassuring. If the engine driving cosmic expansion is not a fixed quantity, but a dynamical field, then the history of the universe told in time is not a fixed story. It is a story written with ink that may have changed color since the first chapters were laid down. There is a question underneath all of this that does not get asked as often as it should. What would it mean for physics if time turned out to be emergent rather than fundamental? What would it mean if the experiments running right now confirm that time is what entanglement looks like from the inside? That the arrow of time is entirely the product of thermodynamic observation? That the universe as a whole has no time but only the appearance of time for the systems embedded in it? The honest answer is that we do not know. Every physical law we have is written in terms of time. Every equation of motion, every differential equation, every Lagrangian and Hamiltonian. The entire mathematical structure of physics takes time as a given and derives everything else from it. If time is emergent, if it is not fundamental but constructed, then those equations are descriptions of a shadow rather than the thing itself. They are approximately correct, the way thermodynamics is approximately correct for large systems, while being strictly inapplicable at the level where time does not exist. A physics without time as a fundamental variable would not look like anything we currently have. It would require not just new equations, but a new conceptual vocabulary, new primitives that do not include time, from which time can be derived under appropriate conditions of complexity and entanglement. The Wheeler-DeWitt equation is the closest we have come to writing such an equation, and the thing it says, when you strip away the technical machinery, is that the quantum state of the universe is not a function of time. It does not evolve, it just is. Static, a single wave function with no parameter t in it. Everything that looks like temporal evolution, everything that looks like change, happening, becoming, all of it is an internal feature of that static wave function. The way the inside of a complex pattern can appear to have movement when you are embedded in the pattern itself. This is what physicists mean when they say time may be emergent. Not that it is an illusion, not that nothing happens, but that happening, change, becoming, these are not features of the fundamental description. They are features of the experience of being inside the fundamental description. And the experience, in physics as in philosophy, turns out to be the hardest thing to explain. It is easier to write down the equations of quantum gravity than to explain why there is something it is like to be a physical system embedded in a quantum gravitational universe. But that experience, that something it is like, is where time lives. And whatever theory eventually explains, time will have to explain that too. The experiments that are running right now are probing this boundary in different ways. ACES is testing whether general relativity holds at the precision level where quantum gravitational corrections might become visible. The nuclear clocks are testing whether the constants are constant. The Piotrkowski-Beauregard protocol is testing whether quantum mechanics and general relativity make the same predictions when applied simultaneously to the same system. The DESI survey is testing whether the geometry of spacetime is evolving in the way our models predict. Each of these is a different angle on the same deep question. Each of them is precise enough that a null result will rule out certain possibilities and a positive result will open new ones. The null results are as important as the positive ones. If ACES finds perfect agreement with general relativity at its precision level, that tells us the scale at which quantum gravitational corrections become important is below what ACES can reach. It narrows the search space. If the nuclear clocks find no drift in the fundamental constants over years of monitoring, that rules out certain classes of dynamical dark energy models and certain cosmological explanations for the Hubble tension. Each non-result is a constraint, and constraints are how physics makes progress even in the absence of dramatic new discoveries. But the positive results are what everyone is watching for. a detection of constant drift at the level the NIST clock can reach would be transformative, not because we would immediately understand what it meant, but because it would be the first direct evidence that the laws of physics are historical, that they have evolved, that time is prior to the laws rather than derived from them. Such a detection would support Smolin's position over Ravelli's, and it would transform the question of the origin of the laws from a philosophical puzzle into an empirical one. You could ask, in principle, what the laws look like at earlier cosmic epochs. You could try to reconstruct the history of physical law the way we currently reconstruct the history of the universe from the cosmic microwave background. A detection of quantum gravitational effects in the Pekovsky protocol would be equally transformative, but in a different direction. It would show that the marriage of quantum mechanics and general relativity produces effects that neither theory predicts on its own. That would be the first hint of the structure of a theory of quantum gravity and the first experimental guidance for what that theory needs to say about time. Right now, theories of quantum gravity, loop quantum gravity, string theory, causal dynamical triangulation are all mathematically consistent but experimentally undifferentiated. They all agree with observation because we have not had observations precise enough to distinguish them. A positive result from the Pekovsky protocol might change that. It might tell us something specific about how quantum and gravitational effects combine, something that only some of the candidate theories get right. These experiments are happening now, not in the next decade, not in the next century, now. The data is being collected, the analysis is being done, and the results, when they come, will either confirm that our current frameworks extend further than expected or reveal the boundary beyond which they break. Either outcome is significant. Either outcome tells us something we did not know before about the nature of time and about the nature of the universe that time, or the appearance of time, is doing its work inside. What I find genuinely moving about all of this, if moving is the right word for a scientific situation, is that every one of the experiments we have discussed is an act of listening. Listening to the universe for signals about its own nature, listening at higher and higher resolution, with better and better instruments, for the faint evidence of structure below the level of our current theories. The clock at NIST is not just a clock. It is an ear pressed to the wall of physics, listening for the sound of something shifting. The nuclear clocks at Gila and in Braunschweig are listening for the long, slow drift of constants over cosmic time. The ACE's mission is listening for the exact frequency at which general relativity stops matching the data. And whatever we hear or do not hear will tell us something true about the universe. Something that was always true and is now, for the first time, accessible to measurement. The clocks are running, the data is accumulating, and somewhere in the gap between what the measurements show and what the theories predict, the actual nature of time is waiting. Not as a mystery to be revealed dramatically in a single moment, but as a structure to be understood piece by piece, result by result, constraint by constraint. The way all scientific understanding actually builds, slowly, carefully, with instruments that get better every decade and questions that get sharper every time a new result comes in. Whether we are close to a fundamental breakthrough or just beginning to map the territory of a problem deeper than anyone currently estimates, that is genuinely unknown. The physicists working on these questions will tell you honestly that they do not know. And that honesty, that willingness to sit with deep uncertainty while continuing to push the measurements further, is what makes this moment in physics worth paying attention to. The numbers still do not add up. The theories still contradict each other about the one thing that underlies all of them. And the most precise clocks ever built are still running, listening for whatever the universe has to say next. There is one more thread worth pulling, because it connects everything we have discussed to a problem that sits at the absolute edge of what physics currently knows how to ask. It is the problem of the initial state, not just why the universe started in a low entropy state, but why there was a state at all, why there was something rather than nothing, and why the something that there was had the specific properties it had, including the capacity to generate, over billions of years of thermodynamic evolution, the kind of complexity that sits here and wonders about its own nature. This is not a new question. Philosophers have asked it for millennia. But what is new is the way physics has been forced to engage with it, not as a philosophical puzzle to be deferred, but as an empirical constraint to be explained. Because the experiments we have been discussing are not just measuring how time behaves, they are, in aggregate, constructing a picture of what kind of universe we live in. A universe where time may be emergent rather than fundamental. where the arrow of time depends on thermodynamic observation, where the constants of nature may be historical rather than eternal, where causality is not absolute at the quantum level, where the past is a construction as much as a record, and where the presence of observers may be not an accidental feature, but a structural requirement of the framework that generates time in the first place. If observers are necessary for time to exist, in the sense that the page-router's mechanism requires internal observers for temporal experience to emerge, then a universe without observers would be, in a very precise sense, timeless. Not a universe where time has not yet started. A universe where the concept of time does not apply. A universe that is, in the terminology of the Wheeler-DeWitt equation, a static quantum state with no before and no after. The emergence of the first observer, whatever that means at the quantum level, the emergence of the first system complex enough to generate a thermodynamic record of its interactions, would then be not just a biological event, but a temporal one. The moment at which time, in the operational sense established by the Oxford and Morava experiments, first began to apply to the universe. Not the moment at which time started flowing, but the moment at which flow became a meaningful concept at all. This is related to, but different from, the anthropic arguments that circulate in discussions of fine-tuning. The anthropic argument says the constants of nature have the values they have because those are the values compatible with observers, and observers are needed to observe anything. The argument we are tracing here is more structural. It says not just that observers are needed to observe the constants, but that observers may be needed for time itself to have a direction, and therefore for the sequence of events that produce those constants to count as a sequence at all. The universe needs something inside it doing the measuring, not just to know what time is, but for time to be the thing that it is. Wheeler asked this in his sharpest formulation. Does the universe have to have an observer in order to exist? Not in order to be known to exist, in order to exist. The delayed choice experiment, which he designed, pushes on this. In the delayed choice experiment, you can set up a measurement after a photon has already passed through a two-slit apparatus, and the choice you make about how to measure it retroactively determines whether the photon went through one slit or both. The quantum mechanics is unambiguous. The measurement determines the history. Not the measurement determines what we know about the history, the measurement determines the history. Wheeler took this to imply that the universe is, in some sense, participatory, that its past is not fixed, independent of the observations that eventually occur in its future. That, in a quantum mechanical universe, the history is not a sequence of events that happened and then got observed. It is a sequence of events that becomes fixed as it gets observed. Retrocausally, backward from the present, which means the universe that exists now, with its specific history and its specific constants and its specific arrow of time, is not just the product of initial conditions propagating forward through time. It is also the product of the observations that have occurred throughout that propagation. The universe is writing its own past as it goes. This sounds like a philosophical position rather than a physical one, but it follows mathematically from the formalism of quantum mechanics. The wave function of the universe, in the many worlds interpretation, branches at each measurement. In the Copenhagen interpretation, measurement collapses the wave function. In the relational interpretation of Ravelli, quantum states are defined only relative to other systems. In all of these interpretations, the act of observation plays a central role in determining what the state of the system is, and the state of the universe includes its past. So the act of observation, in a very direct sense, shapes the past. Wheeler's delayed choice experiment demonstrates this for individual photons. The Morava experiment demonstrates it for time itself. The Oxford quantum clock experiment demonstrates it for the arrow of time. And the NIST clock, with its sensitivity to drifting constants, is potentially measuring whether the laws themselves are fixed or whether they are part of what gets constructed as the universe observes itself. All of these threads lead to the same place, not to an answer, but to a boundary. The boundary between the physics we have and the physics we need. The physics we have is extraordinarily precise and extraordinarily successful at predicting observations. It has given us GPS, navigation, and transistors and lasers, and the entire edifice of modern technology. But it does not tell us what time is. It does not tell us why time has a direction. It does not tell us whether time is fundamental or emergent. It does not tell us whether the laws of physics are eternal or historical. It does not tell us why the initial conditions were what they were. And it does not tell us whether observers are an incidental feature of a universe that would have existed without them, or a structural requirement of a universe that generates time through the act of self-observation. These are not questions at the edge of physics that clever experiments will soon resolve. They are questions at the center of physics, questions whose answers will require not just new data, but new concepts, new ways of thinking about what it means for something to be real, to exist, to happen, to be before or after something else. The kind of conceptual revolution that happened when Einstein replaced absolute time with relative time, and when quantum mechanics replaced deterministic trajectories with probability amplitudes. Those revolutions were not just technical advances, they were changes in the conceptual vocabulary of physics. They required new primitives, new ways of framing what a question about nature even means. The next revolution, whatever it is, will need to be at least as deep. It will need to say something coherent about what time is in a universe where the Wheeler-DeWitt equation says there is none, where the Morava experiment says it exists only for internal observers, where the Oxford experiment says its arrow is a product of thermodynamic observation, where the nuclear clocks are checking whether its underlying constants are stable, and where the Hubble tension suggests our understanding of its cosmic history may be built on assumptions that are not fully correct. The physicists working on these problems are not confused or lost. They are doing what physicists always do at the frontier. They are making precise measurements, they are building mathematical frameworks, they are testing predictions, they are comparing results. And they are sitting with the honest uncertainty of knowing that the next major result might confirm that we are close to a synthesis, or might reveal that the problem is significantly deeper than it currently appears. The history of physics suggests that the deep problems, the ones that seem to ramify rather than resolve as you probe them more carefully, are usually pointing at something genuinely fundamental that the existing framework is not equipped to describe. The ultraviolet catastrophe of 1900, where classical physics predicted that hot objects should radiate infinite energy at short wavelengths, looked like a technical problem. It was a signal that classical physics had reached its limit and quantum mechanics was needed. The Mercury perihelion anomaly in the 19th century, where Newtonian gravity failed to fully account for the orbit of Mercury, looked like a measurement artifact. It was a signal that Newtonian gravity had reached its limit and general relativity was needed. The 5 sigma disagreement between two measurements of the Hubble constant and the suggestion from the NIST clock that fundamental constants may be drifting may or may not be signals of the same kind. But the history suggests that when precise experiments consistently refuse to agree with precise theories, the theories need to grow. What the new theory will say about time is genuinely unknown. It might say that time is what entanglement looks like from the inside and derive the 4-dimensional structure of space-time from quantum information. It might say that time is fundamental and the laws of physics are historical, evolving through something like natural selection of universes. It might say that the Wheeler-DeWitt equation was right all along and time is an approximate concept that emerges from the quantum state of the universe in the same way that temperature emerges from the motion of molecules. It might say something none of these, something that requires conceptual tools that do not currently exist. But whatever it says, it will have to account for all of the experimental results we have been discussing. The GPS corrections, the gyromillimeter result, the Oxford quantum clock, the Morava experiment, the Babar and T2K asymmetries, the quantum Zeno effect, the nuclear clock precision, the Hubble tension, the Deci dark energy evolution, all of it, together, consistently, without remainder. That is the standard by which the next theory will be judged. Not elegance alone, not mathematical consistency alone, all the data. And the data keeps coming in. The clocks keep running. And the universe, whatever it turns out to be at its deepest level, keeps doing whatever it is that it does when no one is looking. Or perhaps, given everything the experiments suggest, it waits until someone is. To understand why the question of time is so resistant to resolution, it helps to trace the specific places where each theoretical framework breaks down. Not in some abstract sense, but concretely. What specific prediction does each theory make that conflicts with what another theory requires? General relativity handles time as a geometric dimension. In Einstein's equations, time is part of the metric tensor, the mathematical object that encodes the shape of space-time. The metric can change from point to point, which is how gravity works. Mass and energy curve the metric, and the curved metric tells other masses and energy how to move. Time, in this framework, bends around massive objects. It flows more slowly, deep in a gravitational well, and more quickly far from any mass. This is not an approximation. The bending of time is as fundamental to general relativity as the bending of space. It is why the theory is called general relativity and not just a theory of space. Both space and time are dynamic. Both respond to the distribution of mass and energy. Both curve. Now take quantum mechanics. In the Schrödinger equation, the equation that describes how quantum states evolve, time appears as an external parameter. It is the variable with respect to which things change, but it is not itself something that the quantum system can act on or be affected by. You cannot measure time from inside a quantum system. You can only use time as the background against which you measure other things. This is what it means to say time is a parameter rather than an observable. An observable is something the quantum system has, something that can be in a superposition, something that can be entangled with other observables. A parameter is something you set from outside before the experiment starts. In quantum mechanics, time is set from outside. It is not part of the quantum system. It is the frame within which the quantum system exists. These two treatments are structurally incompatible. General relativity says time is a dynamic, physical, geometric thing that can be curved and stretched, and that varies from point to point in a gravitational field. Quantum mechanics says time is an external, non-dynamic, non-observable parameter that cannot be part of the quantum system. You cannot have both simultaneously. A theory that combines them has to resolve this contradiction somehow, and every attempt to resolve it has produced something unexpected. The Wheeler-DeWitt equation, as we discussed, resolves it by making time disappear entirely from the global description of the universe. This preserves the quantum mechanical structure by making the wave function of the universe a function not of time but of geometry. The universe is described not as a state evolving in time, but as a static superposition of different geometric configurations of space. Time, if it appears at all, appears as something that can be read off from the geometry in specific limiting cases, not as a fundamental input to the equation. Loop quantum gravity, the framework Ravelli developed with Smolin starting in 1988, takes this seriously and tries to build a complete theory of gravity on the assumption that time is not fundamental. Space is quantized in loop quantum gravity, made of discrete chunks called spin networks. These chunks have geometric properties but no inherent temporal properties. Time, in this framework, emerges from the network of causal relations between quantum events. It is not the background, it is the ordering. String theory takes a different approach. In its most developed form, through something called the anti-de Sitter space/conformal field theory correspondence, discovered by Juan Maldacena in 1997, a gravitational theory in a higher dimensional curved space is equivalent to a quantum field theory on the lower dimensional boundary of that space. The gravitational theory includes time as a geometric dimension. The boundary quantum field theory has its own time, which is not the same as the gravitational time, but is related to it by the equivalence. This duality does not resolve the question of what time fundamentally is. It relates two different descriptions of what time is in two different frameworks and shows they are equivalent, but it does not tell you which, if either, is the more fundamental description. Each of these approaches makes predictions. Loop quantum gravity predicts that the fabric of space-time is grainy at the Planck scale, approximately 10 to the power of -35 meters. It predicts that high-energy gamma rays traveling over cosmological distances should arrive slightly later than low-energy ones, because the higher-energy photons interact more strongly with the quantum foam of spacetime. The Fermi Space Telescope has been searching for this effect for over a decade and has not definitively detected it, which constrains but does not yet rule out loop quantum gravity predictions. String theory in its various forms predicts the existence of supersymmetric partner particles for each known particle, none of which have been detected at the Large Hadron Collider at the energy scales where they were expected to appear. This constrains but does not rule out string theory, because the theory has enough free parameters that the absence of supersymmetric partners at current energies can be accommodated. The experiments we discussed earlier, ACEs, nuclear clocks, the Pekovsky protocol, are relevant to these theories in different ways. ACEs test the precision of the metric near Earth, where loop, quantum gravity, and string theory are both expected to reduce to standard general relativity. A deviation from general relativity at ACEs precision would be more surprising than expected from either quantum gravity framework and would suggest a modification of gravity at scales where current theories predict no modification. Nuclear clocks test the constancy of fundamental constants. Most quantum gravity theories do not directly predict constant drift at the observable level, but some extensions of these theories involving dynamical dark energy or extra dimensions that are evolving do. And the Piotrkowski protocol tests what happens when you put a quantum clock in a genuine quantum superposition of gravitational environments, which is a regime that no quantum gravity theory has produced clear, unambiguous predictions for. A result from the Piotrkowski protocol that disagrees with what general relativity and quantum mechanics independently predict would be direct experimental guidance, the first of its kind for whatever comes next. What is striking about the current situation in physics is not that we have no ideas, it is that we have too many ideas, each internally consistent, each capable of accommodating most of the available data, but none clearly superior to the others. The experiments that can discriminate between them are running now, and the results will arrive over the next decade. This is actually an unusual situation in the history of physics. Usually, the theory arrives before the experiments catch up to it. Quantum mechanics was theoretically developed before many of its most striking predictions were confirmed. General relativity was theoretically complete before the precision technology needed to test it at interesting levels was available. Right now, the theoretical landscape is not settled. There is no single leading framework that everyone is waiting for the experiments to confirm. There are multiple competing frameworks, all of them incomplete, all of them waiting for the experiments to eliminate some of the possibilities and favor others. Which means the experiments are not just confirmation exercises, they are genuine guides. The data coming in over the next 10 years will not just test theories, it will shape what theories get developed. If ACES finds agreement with general relativity to its precision limit, theorists know that quantum gravitational corrections are smaller than that level. If nuclear clocks find constant drift, theorists need to explain what is driving it. If the Piotrkowski protocol produces results inconsistent with both quantum mechanics and general relativity taken separately, theorists have to build something new that covers both. The experiments are not waiting on the theory is waiting on the experiments, and that, historically, is when physics advances fastest. The thorium-229 nuclear clock deserves particular attention here, not just for its precision, but for what it is measuring. The transition in thorium-229, the one that makes it useful as a clock, is called an isomeric transition. The nucleus has an excited state that sits unusually close in energy to the ground state, within a few electron volts, which is the energy range accessible to optical lasers. This makes it the only known nuclear transition that can be driven by optical light, which is the key to making it a practical clock. But what makes it scientifically extraordinary is the sensitivity of this transition energy to the values of fundamental constants. The energy gap between the ground state and the excited state depends on the interplay of the electromagnetic force, which pushes the protons apart, and the strong nuclear force, which holds them together. The precise value of the gap is exquisitely sensitive to the ratio of these two forces. If the fine structure constant or the strong coupling constant drift over cosmological time, the resonance frequency of the thorium transition changes. By how much depends on the size of the drift, but the sensitivity is such that drifts at the level of 1 part in 10 to the power of 19 per year, which is far beyond what atomic clocks can detect, would produce measurable shifts in the thorium resonance over years of monitoring. This is not just unprecedented precision, it is a qualitatively new capability. The ability to detect changes in the constants at levels that connect to theoretical predictions about the evolution of the universe that were previously entirely beyond experimental reach. The nuclear clock was first demonstrated in 2024 at Gela and the Physikalische Technische Bundesanstalt. The demonstration showed that the clock works, that the transition can be driven with lasers, that the frequency can be measured, and that the precision is approaching the level where fundamental physics becomes accessible. Over the next several years, as the clock matures and systematic uncertainties are reduced, it will become sensitive enough to answer the question the NIST aluminium clock is already beginning to approach. Are the constants constant? The answer, whatever it turns out to be, will either close one chapter of the question of what time is or open a new one. If the constants are not constant, the immediate question is, what is driving the drift? The most natural explanation would be some scalar field, a dynamical entity that pervades all of space and evolves slowly over cosmic time, coupling to the fundamental constants and changing their values as it evolves. Such fields are predicted by some extensions of the Standard Model and by some approaches to dark energy. If the nuclear clock detects a drift, it will be the first direct observational evidence for such a field, and the pattern of the drift will constrain what kind of field it is. That constraint will feed back into the Hubble tension, into the DESI dark energy results, into the question of whether the initial conditions of the universe were fixed or selected, into everything we have been discussing. Physics is a single connected body of knowledge. A result anywhere in it eventually touches everything else. This is perhaps the deepest reason to pay attention to the question of time right now. Not because time is philosophically puzzling, although it is, not because the experiments are impressive, although they are, but because the question of what time is connects, without exception, to every other deep question in physics. What is the nature of quantum mechanics? What is the source of the arrow of time? What are the fundamental constants, and why do they have the values they have? What is dark energy, and is it constant or evolving? What happened at the Big Bang, and was there a before? What is the relationship between quantum mechanics and gravity? All of these questions are aspects of the same question. They are the same question approached from different experimental angles and different theoretical frameworks. And the answer, if one arrives, will be an answer to all of them simultaneously. That is what makes this moment in physics different from other moments of active research. The questions being asked are not isolated, they are convergent. They are all pointing at the same unknown. And the experiments running now are the most sensitive instruments ever aimed at that unknown. Whether the unknown yields to the instruments in this generation or the next, whether it requires a theoretical breakthrough that has not happened yet or can be resolved with tools already in hand, whether the answer will be recognizable in the vocabulary we currently have or will require a conceptual revolution as profound as quantum mechanics, none of that is settled. What is settled is that the question is real, that the experiments are running, and that the data is coming in. The clocks are running. The universe is doing whatever it does when it is not being observed, assuming it does anything at all. And the question of what time is remains exactly where it has always been, at the center of physics, unanswered, pointed at by every instrument we have ever built that was precise enough to see it, waiting. If conversations like this one matter to you, and the underlying science here genuinely deserves more attention than it usually gets, consider sharing this video and subscribing so you do not miss what comes next as these experiments continue to produce results. The story of what time actually is, whatever it turns out to be, is still being written, and every result that comes in brings us either closer to the answer or closer to a better version of the question. There is one final piece that deserves to be said, because it runs beneath all of the experiments and all of the frameworks and all of the disagreements between theorists. It is the piece that connects the science to the experience of being someone who thinks about the science. Every person who has ever thought carefully about time has eventually arrived at the same feeling. Not quite confusion, not quite awe, but something in between. The feeling that the concept you have used every day without thought, the concept that structures every sentence you have ever spoken, every plan you have ever made, every memory you have ever accessed, is somehow less solid than it seemed. That the thing you have been calling time is something you cannot quite see directly, cannot quite define cleanly, cannot quite separate from the experience of being you in a world where things happen. The physicists working on the experiments we have discussed are not immune to this feeling. If anything, the more precisely they measure, the more intensely they feel it. Ravelli writes about this, Smolin writes about this, Wheeler wrote about it throughout his career. The feeling that the closer you look, the more time dissolves into something else, interrelations between events, into the thermodynamic cost of observation, into entanglement, into the quantum state of the universe, into the act of remembering, into the structure of physical law, into the past hypothesis, into the geometry of matter. All of these are things that time dissolves into when you push on it hard enough. None of them is clearly time itself, and yet something in our experience of reality feels unmistakably temporal, something that does not reduce to entanglement or entropy or causal ordering without remainder, something that the equations capture only approximately, only statistically, only from the inside. That remainder, the part of time that is not captured by the equations, is not evidence that the equations are wrong. It is evidence that something important is still being left out. It is the same kind of remainder that existed before quantum mechanics, when classical physics could describe the behavior of atoms but could not account for the stability of the atom or the specific frequencies of light it emitted. The remainder was not an illusion. It was a signal. It told physicists that something was missing from the framework, and the something that was missing turned out to require an entirely new way of thinking about the microscopic world. The remainder in our current understanding of time may be pointing at something similar, Not that our current frameworks are wrong, but that they are incomplete in a way that will require genuinely new thinking to address. The experiments running now are not just measuring time more precisely, they are mapping the boundary of what our current frameworks can account for. They are identifying where the remainder lives, and in doing so, they are providing the empirical evidence that will eventually force the new thinking into existence. What the new thinking will say, how it will describe time, what it will take as fundamental, and what it will treat as emergent, what it will say about the relationship between observation and reality, between entropy and history, between quantum correlations and the geometry of spacetime, none of that is settled. None of that is even clearly outlined yet. The experiments are ahead of the theory in precisely the domain where the theory is most needed. And that is exactly the situation in which new theory tends to emerge. The clocks are running, the numbers still do not add up, and somewhere in the gap between what the measurements show and what the theories predict, the actual nature of time is waiting, not passively, not statically, but in whatever way a thing that might itself be the product of measurement can wait for the next measurement to arrive.